Good morning. This is M. Paramesh, convener of 5-day online faculty development program on recent advances in electrical engineering. Welcome you all for the day 3 session. On behalf of Department of Electrical and Electronics Engineering, Gates Institute of Technology, I thank each and everyone for your active participation for day 2 session. I hope you all had an interesting and knowledgeable session on day 3 on recent trends in condition monitoring and fault diagnosis of power transformers by Dr. Rangaraj Chilka sir. It was an excellent research topic on power transformers, and I hope all of us get new ideas by the end of this 5-day FDP. Now it's time to start our today's session. Now I would like to request Mr. Lakshmanath sir to introduce today's speaker.
Thank you, sir. I am M. Lakshmanath, Assistant Professor, Department of EEE. It's my pleasure to take this opportunity to invite an eminent speaker, Dr. Manoranjan Sahu. Dr. Sahu is serving as Assistant Professor in the Department of EEE, NIT Tiruchirappalli since May 2018. Prior to that, he started his teaching career as Assistant Professor in the Department of Electrical Engineering, NIT Meghalaya in January 2018. Dr. Sahu did his bachelor's in Electrical and Electronics Engineering from BPUT Roorkela in 2011, master's in Power Electronics and Power Systems from IIT Hyderabad in 2015. He received PhD in Electrical Engineering from IIT Hyderabad in 2017. During his PhD, Dr. Sahu received the Excellence in Research awarded for years 2016 and 2017 respectively at IIT Hyderabad. He has received the Best Paper Award at ANSYS Convergence Conference, Bangalore in 2014. His areas of expertise include power electronics converter design, single stage buck boost DC-AC converter, PWM inverter, multi-level inverter, induction motor drives, power electronics, power converter for electric vehicle applications. He has around 17 publications in international journals and conferences. His work is highly recognized by the research community. Dr. Sahu is also co-principal investigator of 2 sponsored research projects worth Rs 2 crores under DST and Ministry of Electronics and Information. So I welcome Dr. Sahu sir to take over this session and enlighten us with his experience. Thank you, sir.
Thank you, Dr. Lakshmi.
It is yours, sir.
Here. Okay. Thank you, Mr. Lakshmanath, for a introduction. So I would like to thank you, the Department of Electrical Engineering, of the Gates Institute of Technology, and for giving me an opportunity to share my thoughts on this topic. So yeah, so today's topic would be this topic of discussion is impedance source inverter for renewable energy integrations. Okay, so why this impedance? So today, before going to the impedance source inverters, today, yeah. So my overview of presentation would be what? So what is the importance of power electronics in renewable energy systems? Why we are so much concerned about power electronics things? And in this power electronics systems, how this impedance source converter came into picture and what is the how to realize it? Okay. So then, what are the basic, again, multi-level structure of this impedance source inverter I discussed. Then what is the need of fault tolerant this impedance source inverter I tell, and if time permits, we'll go to the higher power level multi-level fault tolerant multi-level inverters. Okay. So before going to the impedance source inverter, let's discuss what is the importance of power electronics in renewable energy system. Okay. So we know our renewable energy. Basically, when we are saying renewable energy means first thing comes into our mind is PV or wind. Okay. So whenever we are thinking of renewable energy sources, we know it follows some daily and seasonal patterns. Daily means suppose throughout the day our sunlight irradiation is not same. It is changing, right? Similarly, throughout the day means up to evening. After the evening, it is we don't have any sunlight. And seasonal pattern means it depends on what are the seasons. Suppose it is in summer, it is a good amount of sunlight will be there. Suppose in rainy season, because of cloud, we have poor quality of radiation, right? Irradiation. Similarly, for wind also, based on the seasons, it is and daily patterns, our availability is different. Wind speed is different. Okay. So that means because our renewable energy means our energy conversion depends on this irradiation and wind speed. Irradiation in case of PV and wind speed in case of wind power. So power availability what also changes. How much we are getting the power, it changes, right? Similarly, in the other hand, if you see the power demand by the consumers, for example, we are the consumers, right? So for us in daytime we don't need much light loads, lighting for whatever we use for lighting, right? But when it comes to the evening and night, we use more lighting loads. Similarly, daytime we may need some different types of electrical loads play majorly in different times, right? So some of the loads will dominate in the morning, some of the load dominate in the evening, some of the loads in the midnight, something like that, right? Similarly, season wise also depends, right? Suppose we don't need an air cooler in the winter season, but in summer we need it. The seasonal patterns also depends, it varies. So the power demand by the consumers throughout the day and throughout the season changes. So power availability by the renewable energy sources is change means it is different. It is not a particular pattern. It is having based on the daily and seasonal pattern. It varies. Similarly, power demand by the consumer also varies. So that means to synchronize both these things, what we need? You cannot go along means only with renewable energy. You need something like what? Some additional backup sources. So what are those? Fuel cell or micro turbine or some batteries also. If you want, you can use it if you have money. Okay. So now, what is the thing here is, so the terminal voltage of, so how to integrate, and the question is, okay, after I have all the sources I am having, and I know my load pattern is different, my source pattern is different, I am getting the energy. Now, how to integrate with the load? Because my terminal voltages of the wind turbine or the photovoltaic plant, fuel cells are quite different, and my load is quite different. Okay, so what to do? You have to what? Direct synchronization with the grid is not preferred, because suppose you have a wind here. Wind is here means directly, suppose the DFI is there, you cannot connect to the grid. You need a in between some power conditioning system. Otherwise, you cannot control the reactive and active power. Similarly, suppose a PV string is here. PV string output is DC. But if you want to connect to the grid, you cannot directly connect to the grid. Because it is a DC, it is AC, so you need to also control the voltage, frequency, phase, all these things. So, for synchronization, that is the criteria. So, we need what? A power conditioning system. Similarly, fuel cell. Got it? So, all these things, what one or another way require what? Power conditioning system, that is called power converter system. Here, in case of wind, because of PV, these are what? These some of the basic power conditioning system required. Okay. So now you can see here in case of wind, when it is converted to the means connected to the grid, synchronized, you need a what? some power electronic structure like this, which is what not only for active power, it is to control the reactive power control. Okay, so all these things what, and frequency, phase, all these things to be controlled. Okay, so for that, this is the similar for PV system. You need what? A power conditioning system, and similar fuel cell you can see here. So we can see a power electronics how it plays a major role for interfacing different sources, renewable sources with the grid or load. Okay. So based on the power electronic structure, so I will discuss only the inverters. So based on the power level of power applications. So it may be of low power application have different types of inverters, and for high power application we may go for different type of inverters. So for the low power applications, where impedance source inverter, switch capacitor based inverter, switch inductor based inverter are the major trends in the research trends in current scenario. Okay, so whereas in the high power application you can see we have two level based inverters are there. Okay, so these are the what the major inverters, impedance source, switch capacitor inverter or switch inductor inverter are major types of inverters which are used in low power applications. Okay, so I'll discuss out of this impedance source inverter, the first one. Okay, so now what is the motivation for this impedance source inverter? So before going to the discussing about the motivation, right? What we need is we understood what the importance of power converter in the renewable energy system, right? So what we saw observe here is we need before a PV string to connect it to the grid. There are two possibilities. One is what? Either I can connect a voltage source inverter followed by a transformer to the grid. Why we need a transformer? I can directly inverter I can connect it to the grid, because not only for isolation, another importance of this transformer is suppose to minimize the string size, because if you want to the grid connected to a voltage source inverter using a voltage source inverter, a PV string to the grid, because voltage source inverter acts as a what? Buck converter, right? So buck converter means what? We know a voltage source inverter what? The output is what? Vm, peak output voltage is M into VDC. The VDC is nothing but by DC link voltage. VDC. Okay. So here modulation index M is what? Varies from here modulation index M is varies from what? 0 to 1. So that means Vm can be less than or equal to VDC. So that is why the voltage source inverter acts as a what? Buck converter. Now I want a 230 volt, suppose a 230 volt phase voltage, right? A single phase in case of the phase voltage 230 volt RMS, right? That means we need the VDC more than that at least, because we cannot assure always it is 230 volt. PV string voltage fluctuates throughout the day, so we may have to increase it to like 400 volt, then or 400 to 450 volt, right? For 230 volt is 330 around 356, right? So 356 is the peak voltage. So 356 means in the input side you need 356 volt input voltage. So you may go to for you can size of the string is what you may have to connect this for 400 volt, which is not see if you increase the string in means PV panel is connected in series, number of PV panel connected in series of PV cells connected in series, if you will increase, the problem is if any cell faults or any PV panel fault, the total string voltage will collapse, right? So that's why we want to minimize what as minimum as possible the series number of cells or panels. We used to do that, right? So, but we need what? If we want to voltage source inverter, we need higher input voltage. Now, but we want string size should be less. So, to compensate that, what we need a step up transformer here. Okay, so that so that we can minimize the string size. Okay, so that is the what on top of isolation transformer we utilize for our stepping up the voltage. But the problem is with this transformer is size, because a line frequency transformer, you know how much is the weight and the size, right? So now the another option is, if I want to avoid this transformer, what I can use? I can use a boost or buck boost converter before to the voltage source inverter. Okay, so this is a boost converter or buck boost converter. Okay, we can use it. Okay, so in that case, this is what not it will solve the boost transformer stepping up the voltage. Then we can minimize the string size length. Okay, and yeah, isolation won't be there, but you can use some other means. What I can say, that is the drawback of the system. Okay, but isolation is there. Okay, apart from that, you can but achieve other things. Okay, so now what is the drawback of the system? Here, you know, whatever the converter system you do it, the efficiency of each converter, let it be 90%. Then what will be the overall efficiency? Suppose this is 90, this is 90%. It will be what? Because of cascading effect, it will be what? 81%. Okay, so as the number of power conditioning stages increases, in the second case, my efficiency what? Coming down. But I am able to what? Compact. I'm not using any transformer. My size of the converter, because of this is a high frequency converter, my size is less compared to the high frequency transformer, and I can able to boost it the voltage. So based on the what is the input, I can go and match the voltage required for the voltage source inverter. But the only drawback is what? The efficiency. Okay. So all these things, after this thinking in picture, I mean coming in picture, what we are saying, we can conclude that the line frequency transformer increases system size for low and medium power application. So that is the limitation of the first case. And the second case, what is the limitation is what? More number of power converter stages decrease the system performance. Okay. On top of this, there is another thing you might be noticed. You might have noticed. Who might have developed the hardware of any voltage source inverter. So you know a typical voltage source inverter, how it looks like. It is a DC source, H bridge. I am saying simple H bridge. This is our switches. So this is my load. Okay. So now this is S1, let S3, S2, S4. So what we used to do? S1 complementary we used to give to S2. Whatever the PWM technique you do, take it. S1 and S2 will be simultaneously turned on for plus VDC. Suppose this may plus for getting plus positive half cycle. If I want to get negative half cycle, what I have to do? S2 and S3. I have to turn it on. Okay. Now what I have to, another thing what we used to do, we used to complement S1 complementary, whatever the pulse is to given to S1, we used to do what? Complementary of S1 to we used to give to S2. Right? Now the thing is here, if in simulation MATLAB nothing, because its transition time is very less, right? From one switching to another state, one switching state to another state. But when we are going for hardware, you see this S1 and S2 are either MOSFET or IGBT you are taking, right? It has its own turn on delay time and turn off delay time, right? But these pulses are coming from what? A gate driver circuit, right? Followed given from a microcontroller. You have to, from microcontroller, you are giving the pulse to the gate driver, then gate driver is giving the gate driving signals, right? So whenever these gate driving signals are coming, okay, these are instantaneous signal is coming now, but S1 turn on and turn off delay time is what? Okay, so I think some internet issues are there. I got the information from some people. Okay, so yeah, if any issues, let me know in between. Okay, fine. So yeah, so what I used to say is, I was saying, yeah, this S1 and S2, the switches will have a turn on and turn off delay time, right? So the turn on and turn off delay time, but your pulse already came, right? So what will happen? It may short circuit the. You need to wait before giving the pulse, because otherwise S1 might have not been turned off properly, but you have given S2 to the pulse. So what will happen? So it will what? Short circuit. Okay. It will short circuit the both the switches. Short circuit the switches, right? It will short circuit. It will short circuit both the S1 and S2. Okay. So S1 and S2 will be what? Short circuited. So to avoid that, what we used to do? We used to give a delay introduced between the consecutive switching pulses. Okay. So and the protection circuit also given between the gate drivers. Okay. Gate driving pulses. Okay. So, but another issue is, okay, you can give a delay circuit, but fine. But the problem is, if you give a delay, what will happen is, suppose we know suppose a sine because our instantaneous output, suppose is what? Suppose we used to give a sinusoidal output is like this, right? Pulse used to get, right? A sine triangle used to be a pulse modulation, right? Used to get like these pulses, right? But if you give a delay, instead of here, you are supposed to get pulse here, you will get what? After some delay. So that means the delay, because of delay, there will be what? Some error in the voltage. Whatever desired and what you are getting, that pulse is what? Some error is there because of some delay. If you are giving some delay to protect the switches and source, to avoid the shoot through, if you are introducing something like this, then what will happen? This will introduce a delay. This delay will what? Cause the voltage error, which will introduce what? THD. Okay, some power quality issues, the total harmonic distortion, harmonic issues in the output voltage. Okay, So now what is our objective is what? How to come up with a converter which can not only serve this buck and boost the input voltage and invert it in a single stage, because this two stage by efficiency degrading. In a single stage, you should be able to do it. At the same time, I should not, I may not require any delay circuit. Okay, what is the need of delay circuit? We saw in a conventional voltage source inverters. But in normal thing, we don't need any, we should not require any delay circuit, right? So, and at the same time, it should be able to buck boost and invert the voltage in a single stage. Okay, so to do that, that is the motivation come into the for the impedance source inverter. Okay, so what it is doing, we have seen this is what DC converter. This is the normal two steps in the last. Now, what is the how to this impedance source come into picture? This will combine the properties of both this converter and make a single converter which will achieve both the objectives. Okay, what is the objectives? One is what? It will boost the buck and boost the input voltage and get the desired output voltage. At the same time, it will not require any delay circuit, or you are get rid of what shoot through. Shoot through means what? What I mean to say is short circuits. Here what? Because of S1 and S2, if it is anytime turned on, we used to avoid it, right? So that is called shoot through state. Okay, that shoot through is what is utilized here. So you don't need any delay circuit. So that is the motivation. So what is the motivation here? Again, I'm saying one is what? Either you have to utilize both the features of DC-DC converter and DCS inverter in a single converter and realize single converter. At the same time, you should what? Get deprived, means you should avoid what? Using delay circuit. Okay. So instead, what we should utilize that shoot through state to boost the voltage. Okay, we'll see one by one. Now, it comes what? How to realize this impedance source inverter. Okay, my voice is audible, and now this it is properly streaming. Means
Yes, sir. Yes, sir.
okay.
No issue, sir. You can carry on.
Okay, so now how to realize this impedance source inverter? Okay, so to go that we need to what? Revisit what the voltage source inverter. It's a H-bridge voltage source inverter. You might be aware of it. So what are the three states of operation? Two states of operation. One is your active state. One is your zero state. So what is the active state? Active state is nothing but VDC is the input. Either it is what? The state where power is transferred from the DC source to the load. Okay, so it may be a plus VDC or plus minus VDC. So the output here at the load, V load, voltage can be plus VDC or minus VDC. Okay, based on the switches. Suppose I want plus VDC, suppose this is my plus minus symbol. So V load will be what? SW1, SW2. If you have to turn on, then VDC will get S1 and S2. SW1, SW2 will turn on, you'll get it. If I want minus VDC, SW3, SW4. Right? Now, this is my active state. Got it? Now, if I want to another state, what is that? Zero state. Zero state means what? This is what? Zero state. So it's exactly what this is. I want to say is normally our design is what? Sinusoidal, right? But when you are going for a sinus pulse width modulation, what we used to do? How the switching is to be done? We used to compare with a triangle. The sine is compared with a triangle, right? So like this. So this is my, when sine is less than the triangle, this is my zero state. Pulse will be zero. So when a sine is greater than the triangle, it is what? Active state. right? And when it is again from here to here, it's 0. Again, when here to here, sign is greater than triangle, like this, right? So these are what? Active state. Active state. And these are what? 0 state, from here to here. 0 state. Okay. Got it? So if I want, this is what positive half cycle. Similar negative half cycle, it will come. Okay. So if I want active state, what is the voltage should be? Plus VDC. This is what? Plus VDC should come. This is what? 0 voltage. So plus VDC means you have to, so AW1, AW2 you have to. If I want minus VDC, you have to AW3, AW4. Okay. Now another state is what? 0 state. So 0 state, what you have to do? You have to turn on what? AW1, AW. Otherwise, voltage across this load will not be 0. Okay. So 0 state means what? You have to either AW1, AW3, you have to turn on, or SW4 and AW2 you have to turn on. Okay. So any two combinations, any of the two you can follow it. Okay, so in this state, no power, you can see, no power is transferred from load to the source. No power. There is no, because here is the open circuit, right? Here is the open circuit. So only whatever the load here it will be. Because if a inductive load, if residual power will be there, so that will be circulating through this. Okay. So that is called what? 0 state. Now, is it only one possible way to get this 0 state? 0 state means what? Voltage across the load is 0, right? No, there is another state. Okay, there is another way also. Okay, so what is that? That is here. Let me erase this thing, then you can visualize properly. Okay. Okay. So now this is my shoot through 0 state. There is another way of 0 state. Okay, so this is not the only AW1, AW3 or AW4. Another is what? I can turn on all the switches of an inverter only. This is also a 0 state. How? You can ask me. Suppose this is what? V load. V load is nothing but my V load. This is my V load, right? So what is the voltage? If it, because we know inverter we are going means what? A inductive, mostly inductive load, right? Inductor will be there, right? You are going for a AC load, right? So if you AC load, DC means whether it is not a matter, right? If it is AC load, means inductive load, what is we have a some? Suppose this is my voltage. Current is what? Somewhat lagging, right? Current is to lag. The voltage becomes 0, but current always what? Lags, right? Current lagging. So whenever the voltage becomes 0, but current is to be there, right? Whenever in an inductive load, right? So what you have to give a path, right? So that is why we are going here. You can ask me, sir, it's just why to turn on AW1 and AW3. I can turn it off, na? Then my current is 0. No, because voltage becomes maybe 0, but what is happening is you are not you are turning off the switches, but the inductor is there. You are suddenly turning off the voltage. Means L di by dt, you are making it what? 0 instantaneously. Okay. So because you are open circuiting the inductive path current, right? If you not do these two things, so that means a huge current will be there. Okay. So it will blast the switch. So you have to give the path for the inductive current. Similarly, that is why I am turning on SW1 and SW3. Similarly, here SW1, SW4, SW. So here, if I turn on both the switches SW1 and SW4, switch 1 and switch 4. So it will what? Suppose before this, my current was flowing like suppose here in this direction. Okay. Got it? to the, suppose it is a positive VDC, it is stable. Now, whenever it is going off, means I want to zero state, from active state to the zero state I am going, then what will have to happen? I have to turn on what? Both LW1 and LW4. Then what will happen? Current will what? Automatically, if it is in this direction, it will take care. LW3 will, anti-parallel diode here will take care. If it is in this direction, then anti-parallel diode of LW, it will go like this. So by this also, the shoot through zero state also we can get a zero state. Normal zero state, this is shoot through zero state. Means what is the difference here? I am turning on both these switches in an inverter leg. Here what? Turning on all the top switches of inverter leg or bottom switches of the inverter leg. Normal zero state. Shoot through zero state is what? Turning on all the switches in a single inverter leg. Okay. So what I mean to say is, so this is another possible way of getting the zero state, but this is avoided in a normal voltage source inverter. Because if I switch on both the switches, what is happening here? It is short circuiting the source VDC. If I turn on LW1 and LW4, means switch 1 and switch 4, or 3 and 2, what is happening? My all switches, it's a VDC short circuited. The resistance in this path is near negligible, current is very high. So it may burn the source, because every source is limited current supplying capacity, right? Similarly, switch also will burn, because if it go beyond the current through the switches is more than the limit, then it will burn. Okay. So you understood now up to what? What is the active state? The normal voltage source inverter. What is zero state? Normal zero state. And what is the normal? Means shoot through zero state, which is avoided. Normal, this is what? Not preferable. Okay. Now come to the, we understood what voltage source inverter. Now come to the what? A normal boost DC-DC converter. Okay. So a boost DC-DC converter, if you see here, is how it behaves. You know, this is a DC-DC boost converter. It is VDC in series with the inductor. Then we have a switch here. Then we have a diode, capacitor, and load. Right. So based on this switch turn on and turn off, my boosting, voltage boosting is to be done. Right. We used to see now. We'll see now. So what are the two operating states? We know one is what? During DTS period, my switch S is what? Turned on. So it is what? Turned on. Switch is what? Turned on here. Turned on. So what will happen? Inductor is what? VDC L. So voltage across the inductor is nothing but VDC plus VDC. So inductor will what? Energize. Inductor what? Here energize. So who will supply the low power to the load during this time? Capacitor. Okay. So capacitor will supply power to the load during this time. So what is the voltage? Diode is what? When it is turning on, so you can see voltage across the diode D1 is nothing but my capacitor voltage. So capacitor voltage means what? What is happening? My diode is what? Reverse biased, and it is what? Turning off. Okay. So what is the voltage across the switch S here during this time? DTS period is 0. You can see 0. That's all the switches is done. Let them consider what? All ideal cases. Okay. So voltage between what? A and B point is what? 0. Now, similarly, this is my A suppose this is AB point. Mentioning AB. Now, when S is off, okay, during 1 minus DTS period, what is happening? Whatever the inductor energy is stored here, it will what? Relax and charge the capacitor, and the remaining power will supply power to the load. So what is the voltage across the switch A and B? Across the switch means it is the voltage between A and B point. Is nothing but my capacitor voltage. Yes or no? Okay. So during 1 minus dTs period, voltage across A and B is what? Same as the capacitor voltage. During dTs period, voltage between A and B is what? 0. Okay. So let now you see now the active state here in the voltage source inverter. So this is my left A point, this is B point, this is A point, this is B point, A point, B point. Now between A and B point, what is the voltage during a active state? It is nothing but my DC link voltage VDC. In the active state, what is the voltage between A and B? Active state, it's VDC. So VDC, so which is equivalent to what? 1 minus dTs. So during 1 minus dTs is equivalent to what? My active state between A and B. Now, what is the voltage in this? So zero state will not go because it is. If you want to go also no problem. Okay, what is the normal zero state? What is the voltage between A and B? It is same as the active state here during 1 minus dTs period. Now, if I going to shoot through zero state, what is the voltage between A and B? It is what? 0, which is equivalent to what here? Shoot through zero state, equivalent to. So, for A and B point, what is the voltage here is 0 in the shoot through zero state. Similarly, here shoot through during dTs period, my voltage between A and B is 0. Now that means, can I replace whatever the devices is here between A and B? This is my A and B here. This is A and B here. Can I replace A and B, whatever devices here, with this structure here? If I replace, then what will happen? It will happen like this. Yes or no? Let me erase. All of you are in line with me. I hope if you have any questions, you can ask me. Okay, anytime you can interrupt me and ask me. Oh, so you can see here my the voltage between A and B is what? 0 during dTs period, which is equivalent to the shoot through zero state, and the active state is the voltage between A and B. DC link voltage is here is equal to capacitor voltage. So I can replace this with what? Inverter leg, and the A and B I can replace with what? Like this. Thanks, please. Okay. So in this, what I have to do during active state, that means when I need 1 minus dTs period, I can turn on S1, AW1, AW2, or AW3, AW4. Okay. And when I need to energize the inductor, what I have to go? I have to turn on all the switches. I have to go to the zero state. Okay. Shoot through the zero state, I need to go. So during dTs, so dTs period is equivalent to shoot through zero state, and 1 minus dTs period is equivalent to what? Active state and normal zero state. Okay. So if you go like this, what will happen? So what is the my VM will be what? My output VM at the output voltage, which is nothing but my M into modulation index into what? The DC link voltage AB. So here, what is the DC link voltage between A and B? It is what? Because here, in case of here, what is the output voltage? M into VDC, right? So where VDC is what? My DC link voltage between DC link voltage between A and B, right? So here, my DC link voltage between A and B is what? Nothing but my capacitor voltage. Because when it is in active state, my A and B voltage is nothing but my capacitor voltage. Diode D1 is to conduct, right? So M into VC is my output voltage. So M into, so what is VC? VC we know The DC what the VC is nothing but VDC by 1 minus D, a boost converter. So if I replace it, then it is what M into VDC by 1 minus D. Okay. So like this, I can realize a boost from a normal boost DC-DC converter and voltage source inverter to a single stage buck boost converter. Okay, single stage buck boost converter like this. Okay. Now, how to go for a modulation? Because the real challenge is how to properly modulate it. Okay. So if you see here, now how to go for a modulation is, this is a sine triangle PWM technique, SPWM technique. Sine triangle PWM technique. Here sine is what? This is my modulating signal. VMT is my modulating signal. Okay. And here the triangle is my what? Carrier signal. So here what you have to do here is, when the modulating signal here, what we should do, compare with the carrier signal. So when the modulating signal is more than the carrier signal, okay, we should go for what? Active state. When the modulating signal is less than the carrier signal, we should go for zero state. You can see here, this is my modulating signal. Modulating signal. This is my what? Triangle is my carrier signal. So I have taken here what? One sample of this, so that for my easy understanding. Okay. So now here you can see the modulating signal is what compared to the carrier signal. So when the modulating signal here is, when sine is greater than the triangle, okay. When the modulating signal is greater than triangle, as I said, it is what? Active state. Okay. When the modulating signal is, or carrier signal is greater than the modulating signal is less than the carrier signal, it is what? Zero state. This is our normal SPWM. We used to go for inverter, HVDC inverter. Right. Now, how to introduce? If I want all full zero state, I can give it to the shoot through state to boost the voltage. Okay. But if I want, because if I want, but this period is what? And the sine wave is varying. So my zero state will be whatever the width of here and here and here, all together. This is here. You can see this width is what varying. So that means my zero state width will vary. Okay. So that my if I want to introduce shoot through zero state here, that width will also vary. So that means my it's a variable duty ratio, shoot through duty ratio. So which may equal, if you want to get a less ripple capacitor voltage, you may need a higher capacitance value. So now if I want to know, I do not want a higher capacitance, if I want to go a low value of capacitance, then what you have to go? You have to use a constant or fixed shoot through duty ratio signal. Okay. So you can see here, if you go for a fixed shoot through duty ratio type of control, then what you have to use? One additional shoot through signal. This is what? Shoot through signal will introduce. So in such a way that you should introduce, its amplitude should be less than the whatever the modulating signal amplitude. Okay. So you can say that modulating signal amplitude is what? From suppose here to here, my modulating signal amplitude M. So and D is what? D is what? My whatever the remaining period. So remaining period from the height of the triangle is will be what? Here it's 1 minus M. So D should be what? Less than equal to what? 1 minus M. Or I can say M should be less than equal, or yeah, M should be less than equal to 1 minus T. Okay. So like this, you have to do it. Okay. So if we do like this, then you can see here how to control it. When modulating signal is greater than this carrier signal, it is what active state. And when modulating signal is less than the carrier signal, then there are two types of zero state experiment. One is normal zero state here, another is what shoot through zero state. So shoot through zero state will come only during when B shoot through is what less than the triangle and greater than this period BM, right? So you have to choose like that. Okay. So this is mine. So you can see here, if I simplify, it's M plus D should be what? Less than equal to. Okay. So modulation index plus shoot through DT ratio, sum should be what? Less than equal to unity. Okay. Now, if this is the modulation index and this is the condition for M plus D should be less than equal to unity. Now, what is this converter? What we gain? What is the gain of this converter is what? M into BC, which M into BD is by 1 minus D. Now, D is what? From the modulating signal. If you are going for fixed duty ratio, shoot through duty ratio, then what we are getting? M plus D should be what? Less than equal to unity, or M is less than equal to 1 minus D, or D is 1 minus M. Okay. So if I am going like this, then we'll put, so maximum voltage of the output voltage is what? Less than equal to VDC. If you are going with fixed duty ratio, if you are going for variable duty ratio, you may increase. Okay. So now how to go more than this gain VDC by 1 minus D, so that my voltage, if you, with the fixed duty ratio also, fixed shoot through duty ratio also, I can boost the voltage. So to go for that, we are coming for what? Z source inverter come into picture. Okay. So let's if you have any queries or you can ask me, or I can continue in 2 minutes.
Sir,
Yeah.
sir, actually participants are in YouTube live, sir.
Oh, okay.
They are posting questions, so
Okay.
we will ask at the end, sir.
Okay, sure. Thank you.
Okay, sir.
Okay. So now, the next thing is what? How to go for the Z source inverter. Okay. What are the limitation of the normal boost derived converter we saw here? Boost derived inverter, single stage inverter. We saw what is the drawback is what? D1 is what? The gain is not as expected. Higher gain. Okay. Boost. Edge boosting is not as expected. Second is what? If you remove the load here, then this capacitor, if you don't have any load, then this voltage will build up. So which may unstable the device. Okay. So that is the another drawback. So to get rid of that, what is the another converter we can see? The Z source inverter. Okay. So how this Z source inverter can be realized? To see that, let us see a DC-DC converter like this. VDC here. How many switches are here? 2 switches are there, and 2 capacitors C1 and C2, 2 inductor L1 and L2. Okay. Right. Now, we'll go on like this. What will happen? If I will switch on S2 and S2 with the DT ratio period of DTS, what will happen? Whatever the capacitor here, C1 will energize this inductor L2. C1 will energize this inductor L2. L1 will be energized by C2. C2 will energize L1. Okay. So the inductor will be what? Energized, and input what is disconnected from the power conditioning stage. S1 is what? Turned off. During this period, what? S2 on, S1 off. Okay. So inductor energizes, Inductor energizes. Inductors are energized. Capacitor are discharged. Okay, in this state. Now, what is the other state? It is a 1 minus dT state, right? Here, what will happen? S1 is on, just complementary to the dTs period. S2 is off. So here, capacitor energized, inductor discharge, de-energized. Okay, so this is the process, right? So you can see here, this is during this period capacitor, you can see VDC along with inductor L1 energizes this capacitor, and VDC along with L2 energizes this capacitor C1. Okay, so C1, C2 energizes supply power to the network. Okay, so now if I go for 1 second balance, okay, so we can get the voltage of VDC. We can get the what? We can get it is what nothing but my VDC into 1 minus D by 1 minus 2. This is the voltage again across capacitor C1 and C2. Both the capacitor voltage will have. Just you can go write the equation for inductor voltage, then you can get it. Okay, like a normal boost converter. So now, if I want to, we know how the switching state, what is the voltage across S1 and current through S1 in DTS period and 1 minus DTS period, and what is the voltage and current through switch S2 during DTS and 1 minus. So we can go for a switch realization. If I go for switch realization, the optimal switching can be what? S1 can be replaced with a diode, S2 can be replaced with a a MOSFET or IGBTs with anti-parallel diodes. Okay, so now as I said earlier, the voltage across the switch here S A and B is what? Changing from, sometimes it is the C2 plus L1, what is the voltage, and sometimes it is 0. So 1 minus DTS is what I can replace with what? Active state and 0 state. And DTS period can be replaced with what? Sweep through 0 state. Sweep through 0 state. So that means this S2 can be replaced with what? A inverter bridge. Okay, so you can see here, this is the same converter here. I am redrawn. Okay, with beautifully, so that my visualization will be easy. So S2, again I have taken toward the outside, so it can be visualized like this. Okay, so now what it can be, S2 can be replaced with what? My S2 can be replaced with what? An inverter. So you can see here, S2 can be replaced with what? Inverter. Okay, so you can see here, this is the S2. So the switch, which is what operated with the DTS period, or which is turned on with the DTS period, that is replaced, not the diode. That is very important. Okay, so the switch S1 here, both the switches S1 and S2, but S1 is turned on for 1 minus DTS period, and turned off for 1 minus DTS period, turn on for the 1 minus DTS, turn off for DTS period. But what you have to replace? The switch which is turned on for DTS time. Okay, switch. So the concept is what? Switch which is turned on for DTS period is replaced by inverter. seconds. Okay, fine. So I can replace the inverter. So what is the operation now? It can go to active state, 0 state and shoot through state. Okay. So active state means what? Like this. I have to get the either plus BDC or here not plus BDC. It is a DC because you may be confused with the DC. Sorry. Let me write in other. So this is my what? A point, B point. So active state means either you will get VAB plus or minus VAB. You will get. Okay. 0 state you will get what? So in active state, what is happening? It is equivalent to, sorry. It is equivalent to what? 1 minus dTs period here. Okay. So here what? Inductor is what? Inductor is de-energized, capacitor is energized. So here also you can see inductor is what? De-energized. So here inductors L1, L2 de-energized, C1, C2 energized, and power is transferred from source to load. Okay. So this is the active state. So either you can turn on SW1, SW2, or you can turn on SW3 and SW4. Any everything. Okay, this is what active state. Now, what is the 0 state? So 0 state means what? Either you have to turn on both the switches of top switches or bottom switches. Okay. So here the voltage is what? 0. So the V load is what? 0 voltage. Okay. So here either what you have to turn on SW1, SW3 or SW4, and the remaining inductor procedure is what? Here also it will work. Same. L1 and L2 de-energize, C1, C2 energize. Okay. So now another state is what? Which is required to boost the energy, that is called shoot to the 0 state. So here in this state, what is happening? I have to turn on either SW1, SW4 or SW3, SW2. Okay. So all the switches in inverter leg, all the switches I am saying turning on. All the switches in inverter leg have turned on. So the voltage across the load becomes what? Here V load also 0. Inductor what here? L1 and L2 energized. C1, C2 de-energized. Okay. So this is the state. Okay. So now if I go for a multi-second balance, and what is the modulation? As I said earlier, you can go with that kind of modulation. And you can see here what VC1 and VC2 is what? VDC into 1 minus D by 1 minus 2D. And the DC link voltage fed to the inverter leg is what? VAB is nothing but VI is what? Nothing but VAB is VDC into 1 minus 2D. Okay. So you can see here peak voltage is what? M into VDC. DC link fed to M into VDC by 1 minus 2D. Okay. So you can see here this M is what here? Here also M plus D should be what? Less than equal to unity. Okay. So even if you do that, you can also boost the voltage. Okay, and invert the boost and invert in the single stage to get the desired AC output. Okay. Now, what is the drawback of this thing? You can see here in shoot through zero state, my input is what? Discontinued from the circuit. So that means input current is what? Zero. So input current is discontinuous, which is not a favorable condition for a battery fed system or a PV system, right? So if you want to go for a continuous current fed this kind of converter, so what you have to go for? You have to go for quasi-jet source inverter. So how the quasi-jet source inverter is realized? So you can see here the quasi-jet source inverter looks like from this DC-DC converter. So you can see here how many switches are here, S1 and S2. How many inductors are here, L1, L2, C1, C2. Okay. So now you can see here similar to that. Here what S1 is what turned on with BTS period. The S2 is what one turned on with during 1 minus BTS period on. Okay, on state I'm saying. So the switch S1 can be replaced with what? By what mechanism you can see can be replaced with a MOSFET, and S2 can be replaced with a diode. Okay, so as I said, the switch which is operated with BTS period can be replaced with what? Inverter leg. So I can replace the inverter leg, and this is my quasi-jet source inverter. So how it operates? It is also operated in 3 states like before: active state, zero state, and shoot through state. In active state, what will happening? This capacitor C1 will what? Energize this. So here also similar case: L1, L2 will de-energize, C1, C2 energize. Both for this zero state and active state. So this is what are the switches which you turn on? AW1, AW2. If you want plus VDC suppose, or plus AB, VAB. This is voltage between plus DC link voltage plus VAB. If I want to, AW3 and AW4 will turn on. If I want, minus VAB. Like this, I can do it. This is my active state. Zero state, what you have to do? Either AW1 and AW3 you have turned on, or AW4 or AW4 and AW2 you have to turn on. Okay. So this is what my zero state. Now what is the shoot through zero state? Shoot through zero state, I have turned on what? Turned on AW1 and AW4 or AW3, AW. So that all the inverter. So only in this case what? L1, L2 energize, C1, C2 de-energize. Okay. So this is the thing. Then what is the DC link voltage? Capacitor voltage VC1 and VC2 will be what? You can see it is not equal voltage. So VC1 will be what? Voltage across the capacitor C1 is nothing but VDC into 1 minus D by 1 minus 2D, and VC2 is what? VDC into D by 1 minus 2D. And what is the voltage VM? VM is what? M into voltage VAB, DC link voltage. M into what is VAB? VAB is nothing but my DC link voltage is M into VDC by 1 minus 2. Okay. So this is the overall voltage gain. Okay. So the prime you can see here now with this kind of converter you can what go for what the quasi Z source converter you can realize, and you can invert and boost the voltage in a single stage. Okay. Now what is the we studied what is two level buck boost single stage inverter, impedance source inverter. Now can we go for impedance source inverter? Multi-level impedance source inverter. Yes. So what is the source? What is the motivation for this? The motivation behind the prime objective behind the multi-level voltage source inverter is you have to minimize the instantaneous error between the required sinusoidal voltage and generated output voltage. How do you minimize that? Now you have seen in a two-level output voltage how it looks like. Suppose my desired output sinusoidal is like this, then my pulsating output voltage is to come like this, right? Sometimes like this. Like this. I am drawing on the first positive half cycle, right? Now you can see here. So suppose during this period you take it, what should my instantaneous voltage should come? It should come like somehow very low well. But what is the output voltage coming? It's plus VDC. And what is the suppose another instant you take from here to here? From here to here you take it. You can see here the instantaneous value is required is this much. But how much you are getting? It's 0. So there is a what? Instantaneous error. Similarly, here what? You can see what is the required voltage is what? So this is. But what is the voltage you are getting? 0 in a two-level voltage. So the instantaneous error between the desired value and the output, what you are getting in a two-level inverter is quite high. So that instantaneous error we do what introduce the harmonics. Okay. So if you are going for a multi-level inverter, suppose compared to here, if you are going for a multi-level inverter, sorry. Suppose I am going for a multi-level inverter, how it looks like? Now suppose you go for a 5-level. Okay, so initially like this VDC, then after some time it is 2 VDC, then it is 2 VDC. Like this system like that, right? So you can see if it is a multi-level kind of structure, my instantaneous error in suppose this is my VDC, this is VDC by 2, this is VDC. So the instantaneous error between the required and the whatever you are getting is what coming down. Okay, so that improves the voltage profile. Okay, so low distortion of the output voltage with less dB by dt. And so at the low distortion you may need what? Low filter requirement. Okay, so filter requirement will be less. And at the distortion is less, so we can go for if a multi-level inverter, if you are going for a distortion is less, we can what? Minimize the switching frequency of operation, because if you are going for more the distortion is there, so there is harmonics. So to shift the harmonics, we used to go for what? Higher switching frequency. Now to operate in higher switching frequency, right? Operate the converter in higher switching frequency. Now, but with the high switching frequency, my switching loss will be more, right? So if I go for a multi-level inverter, then what if my distortion is less, then I can compromise on the switching. So I can come down the switching frequency so that my switching loss can be minimized. Okay, so that is the logic behind why it is having we can operate in relatively lower switching frequency. Okay, So let us discuss about what two types of multi-level impedance source inverter. One is neutral point clamped impedance source inverter and cascaded impedance source inverter. Okay. So what is the neutral point clamped impedance source inverter? You can see here. This is our Z source unit, right? So if I want a classical, this is actually classical thing. Okay. Now the modern converters have come up with different structure, right? So now you can see if I have only a 3 level, I need what? 2 basic unit of Z source converter, right? Similarly, if I want to go for a 3 level quasi Z source, you need what? 2 basic unit of quasi Z source converter. So if you can see, but we can get the 3 level output voltage, but the problem is the number of passive components is quite high. You can see here how many inductors, the 4 inductors and 4 capacitors. Here also 4 capacitors. Okay. So number of passive components is quite high, right? So we make the system more bulky, right? So to get rid of that, what we can go for is, similarly here you can see cascaded the Z source inverter and cascaded quasi Z source inverter, right? To get rid of the high number of passive components, there is another converter is LC switch multi-level inverter we can do. So instead of the passive components, if it can be replaced with some of the switches, then the size can be minimized. So that is the prime objective. So how to realize that? To realize that converter, you can see here, this is a bridge DC-DC converter, right? You might have studied. This is 4 switches is to be there: S1, S2, S3, and S2. So S1 and S2 operate simultaneously, and S2, S3 and S4 simultaneously they used to operate. So this is these 2 pair of switches. Okay. So you can this is H bridge. Got it. Now how this operates, you can see. So here S1 and S2, you can see here operate in DTS period. Okay. So here what will happen in this period? In this period, inductor L1 energize, C1 de-energize. Okay. C1 de-energized. So, and during 1 minute DTS period, here what will happen? L1 de-energize, L1 de-energize, C1 energize. Okay, and here power is okay. You can see. Got it. So if I go for a 1 second balance, what is the voltage VC1? VDC by 1 minus 2. Got it? Okay. So if this is the case, then you can see here how we can, if you know the switches current and voltage profile, I can replace the S1 and S2 with what? The MOSFET and IGBT, and S3 and S4 can be replaced with what? Diodes. Okay. So with this, now what are the switches are operated with the DTS period? S1 and S2 are operated with the DTS period, right? So you can see here, let me erase this thing so that it will be visualized properly. You can see here, S1 and S2 are operated with what? DTS period. Now these S1 and S2, then what can be replaced with what? Inverter like, as I said earlier. So if I replace, S1 with inverter leg, then S2 with inverter leg, then how it will look like, you can see here, it will look like this. Okay. Similarly, if I want to replace S1 also can be replaced with inverter leg. That is your case 2. So two possible inverter structures can be switch boost inverter can be realized. Okay. So this is called switch boost inverters, and you can see current fed boost inverter. You can say okay. So these two inverters now can be realized, right? Now if you look into properly this device, what is the voltage BC? Is BDC by 1 minus 2D. So what is the output voltage can be M into BC. So M into BDC by 1 minus 2D. Okay. So now if you see properly, look into these two converter, you see how you can observe a good thing here. You can see after switch realization, how this converter is looks like this. It is coming. Okay. Now after switch realization, we have, as I said, these two inverter will look like what? Like this. One is S1 can be replaced with inverter leg. One is what? S2 can be replaced with inverter leg. Okay. So if you see, this is a two inverter. You got it case from the case 1 and case 2. If you see these two inverters are what? Look symmetrical in nature. If it is look symmetrical, can I merge these two converters? Yes, I can merge, I can get it. This is the converter. Okay. So this is nothing but a 3-level LC switch. Here, the passive number of passive components is nearly half of the Z source and quasi Z source. Okay. Now, if I go to the operating modes, what are the 3 states? One is what? Active state, another is 0 state, and super 0 state. So in active state, as I said, what will happen here? Inductor will de-energize, capacitor will what? Energize. Okay. And what is the voltage here? So based on if I want plus VDC, so either put off SW1, SW2, SW11, SW12, if I want plus VDC, plus DC1 in this case. If I want SW12 and SW14 will be turned on then if I want minus VC. So this top and bottom switches, if I want, top switches will be plus VDC or VC1, minus bottom switches will be for minus negative voltage, right? And if I want 0 voltage, what? This is a 0 state. Here what? SW12, middle 2 switches. For a single phase leg, I am saying. Okay. Similarly, through state, what? I have turned on all the switches. So here what will happen? L1, L2, for the L will what? Energize. C will what? De-energize. Capacitor de-energize. Okay. You can see here, not only capacitor de-energize, so you can see another beautiful observation you can see here. Both capacitor and VDC together in series are energizing the inductor. Okay. So now here the capacitor and the VDC in series, addition of VDC and VC2 are energizing the inductor. That's why it is voltage is more than the normal conventional boost converter, DC-DC converter. Okay. So the boost factor is quite high in this converter. Okay. Now what is the switching combination? In general, if I say, so if I want active state plus VD out means plus DC link voltage VI, I want to turn on what? Top 2 switches. If I want to get minus VD to minus DC link voltage, I have to turn on both what? Bottom 2 switches. If I want 0 voltage, what I have to do? So there are 0 state means what? 2 types of 0 state. One is what? Through 0 state and normal 0 state. If I have normal 0 state, you have to turn on what? Middle 2 switches. You have to turn on what? Middle 2 switches. If I want zero state, shoot through zero state, I have to turn on what? All the, either in any one leg, all the switches. Okay. So that is what the operating procedure of this converter. Now, if I go for a voltage across the, if I want to find out the voltage across the capacitor C1, C2, how it look like? So VC1 and VC2 will be what? VC1. Okay, VC1 and VC2 will be nothing but VDC by 1 minus 2D. And the output peak voltage will be what? M into VC, so M into VC. So what is the voltage gain factor here? M by 1 minus 2D. Okay. So if I plot, there are what? M, D and G. If I plot the voltage gain versus modulation D, you can see a 3-dimensional plot. So based on what switching frequency and what switching loss and what are the operating conditions, you can choose an appropriate point out of this device. Okay. So that you can get a desired output. Okay. So how to design the passive components? L1, based on this, just from the ripple, you can see. So you can based on the switching frequency and the ratio and what the ripple you want and what is the capacitor voltage you want. So based on our input voltage, you can design the inductors and capacitors. Okay. So PWM control is easy as usual. So you can see here for F here it has been shown for only A phase. So you can see VA for V minus VA we have taken is a unipolar PWM technique we have taken, and VST and V minus VST is what for the shoot through, constant shoot through. Okay. So you just, as I said earlier, you have to compare the sign with the, this is what VN minus sign, it's a VN minus VR what modulating signal. Modulating signal. And this is what carrier signal. Just compare it and get it. Okay. So this is the switching points. So it has been tested with what for the 110 volt output from the 40 volt input, and you can see here the output. Okay. So this is the DC voltage 40 volt and input current continuous in nature. So it is boosted, the input voltage, capacitor voltage is boosted, you can see, and you can see here the 3-level output voltage, phase, pole voltage, and phase voltage is here. Okay, and line voltage is here. Okay. And you can see this converter can be developed with a basic discrete components like diodes and DC regulators for the gate driver circuits, and these are the IGBTs. This is what with the anti-parallel diode, without anti-parallel diode, gate drivers, and this buffer for protecting the microcontroller. Okay. So from this, I can summarize what it is able to boost the input DC voltage and give required 3-level AC output in a single stage, unlike conventional neutral point clamp voltage source. It will utilizes this through state for boosting of the voltage. In comparison to 3-level conventional neutral point clamp jet source inverter and neutral point clamp capacitor, it uses single split DC source as a less number of high power passive components, which is in weight and size reduction. Okay. So continuous current obviously will have its own advantages, so which will be beneficial for fuel cell EPS system and PV system. And you can see the experimental is matched with the simulation results. Okay. Now let us discuss briefly about the fault tolerant LC switch inverter. Why we are going for a fault tolerant thing of this kind of inverter? Though we have minimized the number of passive components, but why we are interested for this fault tolerant? You can see these impedance inverters are what used for boost inverters. You can see any boost converter is what is boosting the voltage. That means indirectly it is boosting the input current. And as the voltage is boosting, many so voltage stress across the device also will increase. Okay, so high as compared to the load rating. Okay, so this increases the chance of inverter switch failure. Okay, so you can see this is a fault tolerant LC switch 3-level inverter. You can see how this is there. So here only one inductor and 2 capacitors are used, and here this SW1, 3 or 2, 3 are the 4-quadrant switches. You can see either it can be relayed with this or this combination. This is not a problem based on your consumption thing and losses and all you can design it, right? So this is also operated in 3 state: active state and 0 state, shoot through state. You can see the active state what? Inverter is de-energized and capacitor is energized, and power is supplied from the source to the load. Zero state is only the difference compared to the active state is no power is supplied to the load, only power is means the load voltage is zero. Apart from that, this inductor energized and de-energized pattern is similar, same. And SUT3 is what? Same as to the normal LC switching inverter. Here, capacitor and DC source will energize the inductor. Okay. So you can see here, the switching pattern is what? If I want active plus VDC, SWX, it's the top switches you top switch you turn on. By minus VDC or minus VDC means DC link voltage, bottom switch you turn. If I want zero state, I would what? This state, middle LW13 or LW2, depending on which phase you are going for. Okay, and if you are going for SUT2 state, what you have to do? You have to turn on all the switches of this inverter. Okay, so that is the switching pattern. Okay, so what is the capacitor voltage? You can see VC1, VC2 is nothing but VG by 1 minus VDC. You can see VDC here. Okay, okay. So this is the voltage. Okay, so now what is the gain factor? Voltage gain factor N by 2 into 1 minus 2B. So you can plot this and find out by appropriately choosing what is the AM for a particular gain. So you have the flexibility, right? And you can design the inductor and capacitor as well. Okay. So now, as we saw, the voltage across the trace, because the capacitor voltage is boosting to very high value, so the voltage trace across the switches is still quite high. Okay, not only this all switches. Now, if it is voltage, so what will happen? The switch may fail, right? So during suppose in this case, I have considered the failing of switches what? LW1 or LW2. So A phase switch is failing, right, upon certain point. Then what will happen? B and C is there, so you can manage with that too. Okay. So you have to change the PWM control. Okay. So you have to appropriately change in the PWM control in such a way that my balanced voltage you get it. So how to do that? Suppose A phase fault is right. What is the thing is we have to do what? Normal case VAN is V0, VBN is your V into minus 2 pi by 3, 120 degree shifted, right? Now whenever A phase fault is there, what you have to do? You have to modify. Now no need to give anything, any voltage to A phase, then modulate signal. B phase what you have to do? It's 5 pi by 6 you have to give, minus 5 pi by 6, and BC you have to give plus 5 by 6. Okay. So that is for A phase fault, right? So you can see here by looking to doing this, we can what? VAB, VBC, VCA, we can manage the voltage, we can balance the voltage. Okay. Now, if you go for a correcting angle, what you have to do? Correction angle, what you are doing? If it is in the healthy mode, what? VA, VB, VC, what? 0, minus 2 by 3, plus 2 by 3. If you phase A loss is there, then what you have to do? You are doing VA is nothing you have to give. Only modification you have to give them to the modulating signal is what? Minus 5 by 6 to the BB and plus 5 by 6 to the BC. If the B phase loss is there, you have to do what? Plus 5 by 6 to the A phase. B phase nothing you have to give because B phase loss is there. So, we see BC you have to give what? Minus 5 by 5 plus 5 by 2. Okay. So similarly, C phase you have to give like this. Got it? So if you do like this, you can get it. So this has been tested for this kind of condition, 48 volt and 110 volt RMS output. Okay. So you can see here how the after the fault it is again getting as we have seen. The voltage is what can be compensated by adjusting the duty ratio, but the power rating is fixed, so we have to operate the converter with low power rating, right? So that's why power is currently we are declaring, but voltage we are maintaining. Okay, you can see here. Okay, so this is also implemented with hardware prototype. Okay, you can see here these are the normal condition and these are post fault condition. Okay, you can see here. Got it. So, but in summary, I can do it. A fault tolerant multi-level voltage source boost inverter is presented, which is able to boost the load DC source voltage to achieve rated 3-level output voltage. Uses 1/4 number of the inductor and half the number of capacitor as used by 3-level capacitors. At the same time, maintains all the advantages, right? And reduces the system size and weight and inherently tolerant shoot-through fault, which causes catastrophic failure to the semiconductor switches. Okay. And maintain the balanced voltage across load at the time of open circuit switch failure in any of the inverter. Okay. So adjusting shoot-through ratio, voltage rating compensated. Okay, and the converter work can be verified with simulation. Okay. So if you have any questions, I'd like to take some questions. Any questions?
Sir,
Yeah.
sir, you can continue, sir. Completed, sir.
Yeah. The time is now, I think. Yeah.
Okay, sir.
Hmm.
Here we have some questions from audience, sir.
Yeah.
Participants. Sir, first question. Among voltage source and voltage and current source inverters, which one is better?
See, it depends on the application, right? What kind of application you are going for. So based on the voltage source inverter, voltage source inverter is easy to handle and control, whereas current source inverter is difficult to control, right? So, but based on the application, if you are going for a renewable application, it is better to go for current source inverter. Okay, voltage source is basically PV. Okay, and if you are going for a drive application, voltage source inverter is better. Okay. And depends actually, again, different types of drives will have different kind of inverters. Okay. Yes. So based on the application it is. Yeah.
Okay, sir. Thank you, sir. One more question, sir. Which type of PWM technique is better among SPWM and SVPWM?
I think space vector PWM is better because you can use better DC, you can utilize better DC link voltage, right? That means your DC link utilization will be better, means you can use higher modulation index and you need less boosting, right? So you don't need to go stress the switches now. So better to use for space vector. So I have discussed here only sine triangle because for easy understanding, basic understanding. Okay, if you want to use for space vector, that is better. Okay, you can go for that.
So last question, sir. Can we implement Z source inverter in fact system?
Yes, people are going for that. Okay, you can go for it.
Okay, so thank you, sir.
Thank you.
We will close this session with the vote of thanks. On behalf of EEE department, I thank Dr. Manoranjan Sahu Garu. We had a very informative session today. Thank you, sir, for accepting our invitation and delivering the lecture.
Thank you.
I also thank each and everyone for your active participation. I request all participants to join for tomorrow's session. Please make use of all these informative sessions. And as a faculty, it's our duty to pass it on to our next generation. Thank you all.
Thank you.
Thank you, sir.
Thank you. So I'm leaving.
Okay, sir. Can leave, sir.